I introduced this last time, uh, I talked about two different kinds of distributed computing, grid computing and cluster computing. Our focus here is going to be on cluster computing because in cluster computing, your computation is performed by an entire cluster of machines such that each individual machine of the cluster is like any other machine in the cluster. So the machines making up the cluster are not very different. In contrast to grid computing, where the machines making up the set of computing devices are very heterogeneous. So I hope you were able to at least find out a little bit about the folding at home and the SETI at home project. Uh, the first project is a project aimed at uh, computing potential structures of protein sequences. So given a protein sequence, made up of 20 or so amino acids, different kinds of amino acids. Can you predict its structure? That's the folding at home project. And it turns out that predicting the structure of a protein by just looking at the sequence of amino acids making up the protein is a very hard problem. And that's why the computation of that problem has to be distributed across an entire grid of machines. We have to model the atomic forces between individual atoms making up the protein, and then we have to keep in mind the 3D structure of different atoms, their orientation, how they interact with water into which the protein is placed. Water is basically the medium which will also influence how the protein folds and so on. So it's a very, very difficult problem in the field of molecular dynamics, and it's done by simulating or generating different possible structures for these linear sequence of amino acids. SETI at home is again a project where you're looking at signals that are coming from, so SETI stands for Search for Extraterrestrial Intelligence, and you're looking at sequences of electromagnetic radiation, converted into bytes that are coming in from outer space, and you're trying to detect whether, this vast amount of data that's coming in really signifies some kind of extraterrestrial intelligence out there in space. So anyway, we're not going to look at grid computing now. We're going to look at cluster computing. And the other assumption that we're going to make about individual nodes making up the cluster is that it's not important for individual machines to be fault tolerant. So individual machines can be fault prone, but looking at the cluster as a whole, uh, even if some machines fail, other machines will carry on their work. So there will be graceful degradation. So the question is, how do we exploit a cluster of machines to carry out this task of distributed indexing? Now, all the modern web search engines like Google, Bing, Baidu, and so on, they use huge clusters of uh, machines in order to build their web index, in order to build their web search index. And these clusters are actually stored in facilities called data centers, which are located at uh, many different locations around the world. So I hope you were able to go back and look up the videos that I referred to last time on Google data centers to get some idea about how huge these centers are, what they look like, and what are the other kinds of issues that uh, other kinds of engineering issues that people face in constructing and also maintaining data centers, including environmental issues, power management issues, and so on. So that's an entirely different domain of study. How do you build and maintain these data centers? But we are just going to assume that we have this huge number of machines. Google is estimated to have about 1 million servers, uh, and each server having on an average 3 cores, so 3 million cores working on the problem of indexing and also some other problems. So we're just going to assume that we have a large group of machines. We're not going to bother about how these data centers are built or constructed or maintained. And these are also just estimates. Google does not publicly release any specific details about how many servers they have and so on. But these are just estimates based on how much they spend on buying servers every quarter and so, figures like that. Nobody except a few people would actually know how many servers they have or how many nodes in their cluster they have. Now, towards the end of last class, I talked about uh, how going for a system that is non-fault tolerant. That means if you have a cluster of nodes such that every node in the cluster has to be functional for the cluster to be functional, then that's going to be a big problem if you have a large number of nodes in your cluster, because if you have 1,000 nodes, for example, it turned out that the probability of the cluster functioning turns out to be about 36%, for even if every individual node in the cluster has a probability of 0.999 that it's working at any time. You still have uh, a higher chance that the cluster will not be functional at any time, because the probabilities get multiplied. Since every machine in the cluster has to be functional, by having such a constraint, you're basically uh, increasing the downtime of the cluster. But if we actually distribute, if we actually go for fault non-fault tolerant systems, fault tolerant systems where individual machines can fail, then we don't really require every single machine to be functional in order for the computation to carry on. The computation can be carried on even if half the machines fail. And of course, as machines fail, they will be replaced by people managing the data center. And if you've seen those videos which I referred to, one of them actually shows a technician going and replacing one of the broken down nodes with a new node. So any questions about this? You can just ignore this exercise. Um, any questions about what this is where we stopped last time? So Google is estimated to have about 10% of the total computing capacity in the world. Given the number of servers they have and the amount of money that they spend every quarter on these clusters, about 10% of the world's computing capacity is estimated to be in Google data centers. Yeah, somebody turned on the microphone, so you have a question that from that side?
No, sir, we don't have questions. You can go ahead.
Okay. So let's now look at how a cluster of machines in a data center would build the web index by distributing the computation of the index. So we are going to assume that there is a master machine in the cluster which is going to direct the indexing job. Okay, so all the other machines in the cluster are going to be worker machines. So they will be the guys who will be actually toiling to do the computation, while this master machine will direct each worker machine what to do. Now, of course, we have to assume that the master machine itself is safe. That means it's not going to fail, because if the master machine fails, then the entire computation is going to fall apart. So we just need one machine to direct the indexing job of the worker machines that needs to be fail safe. But the worker machines don't have to be fail safe. They can fail um, without actually injuring the computation. And Speaking overall, we'll be breaking up the overall problem of indexing into a set of smaller parallel tasks such that each worker machine can be assigned one of the parallel tasks, and all the worker machines that are assigned tasks will carry them out in parallel. And as one of the worker machines finishes its task, the master machine is going to assign it a new task. So any worker machine that's idle will be assigned a new task. And these worker machines are going to carry out two kinds of parallel tasks. The first task is that of parsing the documents and generating the sequence of term comma doc ID pairs. Right? So recall that the input to the indexer is a stream of term comma doc ID pairs. And these terms are actually normalized. So we are assuming that as the documents are parsed, they are also every token in the document is normalized to a term, and then we have these resulting term comma doc ID pairs generated from the parsing stage. Okay, but implicitly the previous stages, tokenization, linguistic preprocessing, etc., will also be done by these parser machines. And the output of the parsers are going to be term comma doc ID pairs again. And then there are going to be other worker machines that will be carrying out the task of inversion. So inversion is the task of taking these term comma doc ID pairs, which are sorted by uh, by doc IDs, right? Initially, before the indexer actually builds the index, the input to the indexer is a stream of term comma doc ID pairs sorted by doc IDs, and then the task of inversion is to sort these ordered pairs not by their doc IDs but by terms. Okay, so for each term, what is the list of doc IDs corresponding to the documents in which that term appears? That's what we have to transform this to. So initially it's sorted by doc ID. Finally, we need it to be sorted by term. So this is the task of inversion, and that is why the index that is built is called an inverted index. You can imagine building an index just on term comma doc IDs where you're sorting uh, where for each document you're building a postings list of terms which appear in the document. Right? Hypothetically, you can think of building such an index as you're parsing the document. That's called a forward index. It's not of much use in IR. It may have some uses, but it's not generally used. So a forward index is an index where for each document you have a list of terms appearing in it. So the vocabulary or um, the dictionary is now going to contain document identifiers, and then you're going to have a list of terms appearing in the documents in the postings list. And you can imagine these lists of terms to be sorted in lexicographic order. So if I want to find out whether a particular term appears in a document or not, I can use the forward index. I can look up the postings list of that document and I can find out whether the term appears in that postings list or not. And if the postings list is sorted by doc ID, sorry, by term, lexicographically by terms, and if it's implemented as an array, then I can use something like binary search to quickly to quickly determine whether or not the term appears in the document. Okay, so what we actually work with is an inverted index where for each term we have a list of documents in which those terms appear, sorted as per doc IDs. So the task of parsing is going to be performed by some worker machines, and the task of inversion is going to be performed by other worker machines. And this is where the sorting step will be involved. Now, how do we parallelize the overall task of indexing? What we will do is we will take the corpus, which we know does not fit into a single machine. We will split apart, we'll break apart the corpus or the collection into what are called splits. So a split is just a chunk of the corpus, a subset of the corpus. And so it's just a subset of documents in the corpus. And the idea of breaking up the collection into splits is similar to the idea of uh, working with blocks in the external sorting algorithm, right? So a block is defined as a unit of data that can comfortably fit into the RAM of a machine, right? Similarly, a split will be small enough that it can fit into the RAM of an individual worker machine. Now, each of the each of the splits that is created from the corpus will be assigned to a parser machine. So these are worker machines that are going to parse the splits that they are handed by the master. And each parser machine is going to read all the documents in its own split, and it's going to generate these term comma doc ID pairs. Now this stream of term comma doc ID pairs is not going to be written randomly into some output file. It's going to be written in a very specific way. There's a diagram over here which will help you understand this better. So what is shown here is the entire corpus, which is split into a number of splits, and each split is assigned to a parser machine, and the parser machine is going to parse the split it is assigned and generate a stream of normalized term comma doc ID pairs. Now these term doc comma doc ID pairs are going to be written in a very specific way into an output. This output will be residing in the hard disk of the parser machine itself. Okay, the stream of term comma doc ID pairs will be residing in the hard disk of the parser itself, but it will be arranged in a particular way. So in this diagram, for example, the stream generated by this machine is partitioned into three parts. In the first part, so the part which is labeled A to F consists of all the term comma doc ID pairs where the terms begin with an A or a B or a C and so on up to F. Okay, this partition consists of those term comma doc ID pairs where the terms lie in the range G to P. That is, they begin with the letter G or H and so on up to P. And similarly, terms falling into the range Q to Z will be placed in this partition. Okay, so the parser is going to write the term comma doc ID pairs into J partitions, and in this diagram J is equal to 3, and each partition is based on what the first letter of the terms is, right? So these are the three possibilities when you have a partition of size 3. Now let's now look at how the inverters or the worker machines assigned the task of inversion will pick this output from the parsers and then generate the inverted index. Now clearly this inverted index is not going to reside on a single machine. right? So each inverter is going to generate a part of the index, and the index as a whole will be partitioned across these inverters. So each inverter is going to build a subset of the index. Now the inverter is going to collect all the term comma doc ID pairs for one term partition. Okay, what that means is, if you look at this inverter for example, it's going to pick up all the term comma doc ID pairs in the A to F partition of this parser. It's also going to pick up all the term comma doc ID pairs in the A to F partition of this parser, and similarly in the A to F partition of all other parsers as well. So all the term comma doc ID pairs starting with uh, the letters A to F will be handled by this inverter. What that means is that the inverted index that this inverter will then construct by sorting the term comma doc ID pairs will be an index whose dictionary consists of terms starting with A to F. So the postings list in the index over here will be postings list for terms in the range A to F. Similarly, there will be some other inverter which will pick up uh, all term comma doc ID pairs where the terms are in the range G to P, and so the index that will be constructed will have dictionary terms in the range G to P. So you can see that the index as a whole is split across these three machines over here. So that's what this means. An inverter is going to collect all the term comma doc ID pairs for one term partition, but this one term partition will be located across multiple parser machines, and so it's going to pick up all those term comma doc ID pairs for that term partition from all the parser machines, and then it's going to sort them and write them to the postings lists. Now this particular task of sorting and writing them to postings lists is exactly like the internal sorting and the external sorting algorithms that we've seen previously. So whatever we've discussed so far prior to distributed indexing is going to be used in this particular step. But you can see that there is this outer distributed framework that is responsible for building the index as a whole, and then we are just invoking the sorting algorithms that we've discussed so far in order to sort this limited subset of term comma doc ID pairs. So are there any questions about this diagram? So the master machine here is what's assigning the worker machines the task of either parsing or uh, carrying out the inversion. Note that worker machines are not specialized, so it's not that there'll be a set of worker machines that will always do parsing or always do inversion. Okay, on the fly the master will decide. It may decide, hey, this machine needs to become a parser and parse this particular split. It may find out at some point that one of the machines it assigned the task of parsing has broken down, or it's too slow. So it's going to then take that task and say and assign it to some other machine. It may tell some other machine that became free that you now become a parser and you take this split and parse it. So the master is what's coordinating all these tasks, and a machine that was performing the task of parsing earlier could be reassigned the task of could be assigned the task of inversion later on once it has completed its task of parsing, and so on. So these roles are dynamically decided and allocated and changed dynamically as machines complete their tasks or fail or slow down for whatever reason.